Hello everyone. Today I am going to explain our mini project, light activated switch using LDR and OPAMP comparator. This circuit is very useful in systems like automatic street lights, solar lamps and home automation. So let's begin. The main objective of our project are to design a light activated switching circuit, to understand how an LDR responds to light, to use an OPAMP 741 as comparator, and finally to control an LED automatically based on light levels. We have also analyzed the entire behavior of the circuit through simulations so we can clearly see how the switching works. A light activated switch is a circuit that turns on or off a load depending on the light present in the environment. This concept is widely used in the street lights, security cameras, solar garden lamps, and smart home automation. In this circuit, the key component is the LDR. Its resistance decreases when the light increases and when the surroundings become dark. We feed this varying voltage to an OPAMP 741, which is used as a comparator. The comparator compares the voltage from the LDR with a fixed reference voltage and decides whether to turn the LED on or off. The components used in our project are very simple. The first component is LDR. It senses the light intensity and its resistance changes accordingly. Other than LDR, we have used OPAMP 741, which is used as a comparator, a potentiometer to set reference voltage, and other minor components are LED, resistor, and power supply. These components together form a very reliable light activated automatic switch. Now let us understand how OPAMP comparator works. The LDR gives a voltage depending on the light level. A potentiometer set a fixed reference voltage. Both of these voltages are fed to the OPAMP's input pins. When the LDR voltage becomes greater than the reference, the OPAMP output goes high and the LED turns on. When the LDR voltage becomes lower, the output goes low and the LED turns off. So the op-amp is basically acting like a threshold detector, deciding whether to activate the LED based on the ambient light. The sensitivity of the circuit can be adjusted simply by rotating the potentiometer.
So now let us see the simulation of a light activity switch using an LDR and 741 op-amp. The LDR and the 1 kilo ohm resistor form a voltage divider network, and the changing light level creates a varying voltage which goes to pin 2 of an op-amp, and a potentiometer of a 250k ohm is uh, set at a reference voltage and is connected to the pin 3 of the 741 op-amp. The op-amp works as a comparator. When the reference voltage at the pin 3 is higher than the LDR voltage at pin 2, the output at the pin 6 goes high and the LED gate turns on. When the LDR voltage is higher, the output goes low and the LED turns off. In this simulation, reducing the light on the LDR increases its resistance and the LED gate turns on. On the increasing the intensity of the light, the voltage gate drops and the LED gets turn off. This shows the working of the simple light activated switch controlled by light intensity.
Simulation results. Here are the simulation results. In light condition, the LDR resistance becomes low and the voltage at the comparator input crosses the reference and the LED turns on. In the dark condition, the LDR resistance becomes high. The voltage drops below the reference and the LED turns off. The simulation clearly shows the switching action and confirms that our design works exactly as expected. The main application and advantages of our project are: the simple project has many real-world applications: automatic street lighting, solar garden lamps, IoT-based automation, security and alarm circuits, day and night detection system. Some advantages are it is simple, low power, cost effective, highly sensitive to light, and the switching point is easily adjustable. To conclude, we successfully designed and simulated a light activated switch using an LDR and a 741 OPAMP. Through this project, we understood how sensor based automation works and how comparators are used to convert analog variations into digital decisions. This concept is the foundation for many smart electronic circuits. Thank you for watching. If you found this explanation helpful, make sure to like and subscribe.